Welcome to 2.2, position, velocity, and acceleration. Um, Now this is a kind of a change from the book. The book is would be 2.3, but I'm not going to follow the book because I think the book does it the wrong way. So I'm going to do it my own way, which is position, velocity, and acceleration first, then the other stuff, arc length and stuff, in the next chapter. So this first part is definitely a reminder. The velocity at time t is equal to the derivative of the vector function, the position function at time t. That's just that's obvious. But however, this isn't really obvious, unless if you've already learned the stuff from 2.3, this 2.3, 2.2 previously. Is v of t, the absolute value of it, is equal to the derivative of s, where s is the arc length. So what's the arc length? The arc length is simply just, if you have a line like this, the arc length is how long the line is from a specific time to another specific time. So in this case, it would be basically this part of the function right here. So this would dictate the arc length of the function. Is the absolute value of v of t, which means you will take the square root of the x of t, or the x prime of t, right, and it's squared, and then the y prime of t squared, and etc. if needed, right? That will be the arc length. So same thing for here. There could be a z prime of t term as well, but I just put dot 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 because you could be doing it in more than 3 dimensions. So you would just take the derivative of whatever you have from this one, and this would kind of, it would kind of be like, what is it called, the fundamental theorem, where you take a derivative of an integral, but not really at the same time. Yeah, you'll just see this is the arc length, so you take the derivative of the arc length function. The derivative of the arc length function is actually also known as the speed of the function. So this is actually the speed, this is the speed of the function, right? And the speed is the derivative of arc length. The absolute value of velocity is also the speed. The derivative of the arc length is the speed. So the derivative of the arc length, the absolute value of the velocity, and the speed, are the 3 of them are the same thing, right? That's what I wanted to say. The acceleration is, this should also be reviewed. The acceleration is the derivative of the velocity, which is the double or the second derivative of the position function. So let's find the velocity and the acceleration of this particle right here. So I'll give you 2 seconds. 2, 1. Okay. So if r of t is that, then r prime of t is v of t, which is the derivative of the first one, 6t, the derivative of the second one, 5 cosine t, and the derivative of the third one, -5 sine t. There you go, simple. Next is the acceleration, which is v prime of t. So v prime of t is equal to a of t, which is equal to, you don't actually have to write down this work, you could just write a of t, and I'm pretty sure that they'll know. But if you remember the AP test, or maybe other standardized tests, they will make you do this work, where they will make you write v, like the fact that you have to understand acceleration is the derivative of the velocity, and velocity is the derivative of the position. Anyways, find the distance traveled. So distance traveled is a little bit harder. Distance traveled is the arc length, which is what I mentioned before. It's this function basically is from 0 to 1 of all of your components, the x component, the y component, the z component. I will basically explain why that works in the next section, but for now, this is the formula that you use, t0 to t1 of all of those derivatives. So we already have all of those derivatives, the 6t, 5 cosine t, and -5 sine t. So what we will do is we will take the integral from t equals 5 to t equals 8 of the square root of the 3 components, 6t plus 5 cosine 5 cosine t all squared plus negative 5 sine t. I'm just going to make it positive because you know that negative times a negative is positive. Let's keep going. This is the acceleration. Find the velocity if the particle is at rest at t equals 2. So the acceleration to velocity, to go from acceleration to velocity, you have to integrate. So the acceleration, the integral of a dt is equal to velocity. So there are a couple of things you can do, but the thing that I'm going to do is I'm going to integrate, and then I'm going to find the c, find the constant. So acceleration is equal to that, so velocity is equal to the integral of acceleration, which is equal to t squared over 2 plus c1, t squared plus c2, and then t minus t squared over 2 plus c3. So what's c1, c2, and c3? Well, if we put 2 in there, we're supposed to get 0, right? So 0, 0, and 0, it has to be equal to 2 squared over 2 plus c1, 2 squared plus c2, and then 2 minus 2 squared over 2 plus c3. So what's 2 squared over 2? What's 2 squared over 2 is 2. 2 squared is 4. And then 2 squared over 2 is 2, so 2 minus 2, that's just 0. So what you will end up getting is c1 equal to negative 2, c2 equal to negative 4, and then c3 is 0. So your vector c is negative 2, negative 4, and 0. So what you, your velocity is t squared over 2 minus 2, t squared minus 4, and then t minus t squared over 2. So let me just rewrite that. Your velocity is equal to t squared over 2 minus 2, t squared minus 4, and t minus t squared over 2. That's it. Simple. Next question. Applications to physics. Applications to physics. I didn't even know that I had this. I'm such a bad teacher. But anyways, if you've learned physics, mechanics already, or if you've learned physics 1, AP Physics 1, you should be pretty well versed in this form. But if you're not, then it's totally fine. So if a particle is shot from a cannon with initial velocity 0 and air resistance negligible, so there's no force contributed from the air resistance, what are the parametric equations describing the particle's motion? So what you have to realize is there is, so let's say we have a just a point right here, and it's going to go in a parabolic motion because that's how our world works. So is the x direction going to change at all? Do you think the x direction is going to change at all because of some external force? Well, we already said that air resistance is negligible, so the x direction shouldn't change. The acceleration of the x direction shouldn't change. Not the x direction. The x direction of the particle will change. But the acceleration shouldn't change at all because there's nothing, like there's no force. There's nothing trying to make it go faster. As opposed to that, there's a something that we experience every day in our Earth, in everywhere, that does have an effect on the particle's y direction, and that's gravity. And gravity, we use it as, or we say it's g, which I mean g for gravity, yay. But also g is measured as 9.8 meters per second, or about 32 feet per, or 9.8 meters per second squared, or about 32 feet per second squared. So if we take up and right as our directions, what we end up getting for the accelerations are acceleration in the x direction and the acceleration in the y direction. The acceleration in the x direction is nothing, 0. The acceleration in the y direction is simply just g, minus g, because it's going down, right? So what's the velocity in the x direction? It's the integral of 0. And in fact, I probably don't even need the vectors. I don't need the vectors at all, because it's just the x direction and the y direction. And the vectors would just be ax and ay. So v would be vx and then vy. But v of x is, yeah, so what I'm talking about is v would be equal to vx and vy, like that. Or this is actually bad function notation. What I should do is I should put this in terms of t. So ax of t, ay of t, something like that. Vx of t is c, right? And in this case, c is v0, so it's initial velocity, right? So v0. In fact, it's not only v0, because if you look at this path right here, that's the initial velocity. That's where it's gonna go. So we want to if we want to decompose it into our horizontal and our vertical directions, right? Our horizontal direction is going, like, let's say it makes an angle theta with the ground. Our horizontal direction is going to be cosine of theta. So cosine of theta, right? And what would vy be? It would be minus g times t plus c. And our plus c is our initial velocity in the y direction, v naught sine of theta. There you go. So that's our velocity in the y, initial velocity in the y, or the velocity function in the y direction. So now what's x of t, and y of t? So x of t is this plus c, right? It's just v naught times cosine theta times t plus c. What's plus c in this case? If we take this to be our reference point at 0, 0, then it's just 0, plus 0, right? So it's v naught cosine theta of t. That's the first parametric equation. V naught, initial velocity, times the cosine of theta, the angle that it makes with the ground, times the time. Y of t is negative 1/2 times gt squared, because that's the integral, plus v naught sine t, or sine theta times t, plus an initial y. So if we take the initial y to be just right here, if we take the initial y to be 0, it will be plus 0. Usually though, you will see it written as y of t is equal to initial y, y0, y naught, plus v naught sine theta t times t, right? Minus 1/2 gt squared. So that's how you evaluate, that's how you get those functions, by integrating the accelerations to get the position functions. So those are the parametric equations for x and y. Now z, there probably won't be any parametric equation for z unless if there's another force that's pushing it to the z direction, which you will see more in electricity and magnetism. But we're not there yet, and the book doesn't mention it, and I don't want to go into physics, so we will just go ahead and do the physics that's in this book for now. So Newton's second law states Newton's second law of motion states that, okay, we're not doing that page, I'm sorry. Anyways, Newton's second law of motion states that the force is equal to the mass times acceleration. So force and acceleration are both functions of time, then the force of the f of t is equal to mass times acceleration of t, right? So this is a chart of the x component of a force with respect to time. So the y component of the force is modeled by the function f sub y of t is equal to 2 times natural log of t. So write the vector function for the force of this object for t equals 0 to t equals 2. Right, so t equals, so what you could see is the force with respect to time is equal to, what's the x? The x is right here. So if the x is right here, then -4, or from 0 to 2 seconds, so this is t in seconds, 0 to 2 seconds, it's just -4. So that's all I have to write down, it's just -4. And then y is 2 times natural log of t. So that's the x component and the y component, right? So what's the vector function for acceleration? The acceleration is, well, the mass is 2 kilograms, so the acceleration is equal to the force divided by the mass, so 1/2 times -4 and 2 natural log of t, which you can simplify that to -2 and natural log of t. So what is the velocity of the function at t equals 2.5 seconds if the initial velocity at t equals 0 seconds is 5 meters per second? It's a little bit hard of a question because you don't know whether or not the velocity is in the x direction or the y direction. So I'm just going to specify that. I'm just going to say velocity of the in the x direction. There you go. So the velocity is the integral of acceleration, which means it is the integral of the acceleration function. So what are we going to get? So if it's just the x direction alone, ax of t is -2. So what you actually end up getting for the acceleration graph, so if we did ax of t for another color, let's say blue, we'll do ax of t. What you get for the graph is you get half, right? So from here to here it's half because -2, and then it goes down kind of half with half slope, so it still hits that in its halfway point, and then you get that. So how much did it decelerate is what we're trying to find. So how much did it how much velocity did it go down by? And to find that, you have to find the area under the curve. So what you get is, well, if this is -2, you'll get -2 times 2, which is 4, right? This is 4 meters per second, or minus, I guess you could say. And then this is, well, -2, this is still 2, this is 1, right? And then this is 0.5. So 2 plus 1 divided by, or, well, 2 plus 1 times 0.5 divided by 2 is equal to 0.75. So the area of this is -0.75. -0.75 meters per second. So -4 minus 0.75 is equal to -4.75, and if you subtract that from 5, you will get the velocity at 2.5 is 0.25 meters per second, and that's the correct answer. So this function does apply, and you'd be able to put that 5 in there, but it only applies up to t equals 2. So once you get v at 2, that's 1, and then you have to use a different function. Namely, you have to use the function a of x, or a sub x of t, from 2 to 3 would be equal to 2t minus 6. So it will be a big headache, and I don't want to do it. So the graphical representation sometimes is the better option. And that's it for today's lesson. I'll see you next time with curvature and arc length.